Hello, when I was watching the FTFE and Simandan collab video, Flat Earther is getting incredibly desperate, which dealt with Brian Logic's commenting on the Pic Gaspard photo taken from Finistrel. I got a few ideas and had some questions. Among many blunders that Brian Logic made, he showed the elevation profile from Finistrel to Pic Gaspard in Google Earth, which should clearly make Pic Gaspard always visible if Earth was flat. The subject that it should always be visible with refraction has been addressed many times by many people. I won't follow quite the same rebuttal path as everyone else. This video, however, goes over the many questions I had at the time, in addition to some interesting details I learned along the way. As pointed out in the collab video, even with standard refraction, Pic Gaspard should still be visible. But it's clearly not because there's another mountain in the way, obscuring it most of the time. Out of a sense of curiosity, I wanted to know what was that specific mountain in the foreground, and can we use it to approximate the atmospheric conditions at the time? I could have approached the problem by relying only on Google Earth and Walter Bisland's Earth Curve Calculator, but I do like the impact of the visual representation from a scene rendering engine more. So it was back to using a few of my tools I developed and using PovRay. To recreate the terrain profile in PovRay for this view, I would need a lot of elevation data with sufficient feature fidelity. Most of it, however, like the Mediterranean Sea, is secondary and does not obstruct the line of sight of the horizon profile. The elevation data for these regions don't need as much detail, so I opted for a lower resolution data set for most of it. I split the view data into 3 regions. Region 1 is a low resolution profile of the overall area, which includes the landscape from Finistrel to Pic Gaspard and slightly beyond both. Region 2 is Finistrel and the mountain ranges that are visible in the foreground. Region 3 is Pic Gaspard itself. This mixed resolution mode is the main reason my recreated image is not a precise copy of the original photo, such as the missing foreground hill on the right side. With the elevation profile data collected from topographicmap.com, I converted it to data points in PovRay with an adjustable effective Earth radius. This allows me to simulate different refractive conditions. Having done a series of renders sweeping the refraction coefficient from k equals 0 to k equals 0.4, I could then compare my renders to the Pic Gaspard picture and estimate the likely average refractive condition if those conditions were as uniform as they are in my render. I looked for an overall shape of the mountain range profile, which appeared to be a shallow bowl with one side slightly curled up. Scrolling back and forth between the likely candidates, I would estimate the refractive conditions to be approximately k equals 0.246, which is labeled as a stable inversion in Walter Bisland's Earth Curve Calculator. I will get back to that specific k value shortly, but first, with a plausible value for the refractive condition obtained, I then set out to determine which of the mountain peaks between the observer and mountain was the one in the foreground. Using the key data points I got from Google Earth's elevation profile and putting them in Walter Bisland's curve calculator, the obvious first choice obstructing peaks that are near Pic Gaspard did not fit. When I tried those, I was getting a k value near 0.8 to 0.9, and changing the refractive conditions kept both Pic Gaspard and the obscuring mountain together. At one point, when the last of the obvious choices still did not pan out, I thought maybe I was doing something wrong, but I kept going smaller and closer. It turns out the mountain peak in question doesn't seem like a possible choice and is more of an anthill in comparison. This lowly 275-meter mountain is sitting at 239 kilometers away from Finistrel. With the foreground mountain located, I could set the 2 objects in Bisland's curve calculator and adjust the coefficient of refraction to compare the tool's rendering against my PovRay recreation. The curve calculator mirrors mine, and mine at k equals 0.246 is most consistent with the relative positions of the mountains in the photo. I may have chosen a single refractive coefficient along the entire distance, but there is one important detail that should be pointed out. The refractive conditions are not uniform, and with that, we can do a bit of digging to uncover an interesting phenomenon. The conditions over the water compared to the conditions over the land are quite unlikely to be the same. They might be slightly lower than the average over the water and slightly higher over the distant mountain ranges. I would venture a guess that the secret sauce that made this picture more likely than just being at the right place at the right time was the many valleys in the foreground along with favorable weather conditions from the day before. Let's examine what a stable inversion is and what might amplify the effect. I want to separate the concept of a temperature inversion from a refractive condition inversion. The glare we see above hot pavement on a summer day is an example of a refractive inversion. Hotter air below colder air with a large enough lapse rate than the air at the surface is less dense than the air further above it. This is inherently unstable and in my example only sustained by the continued presence of the heat from the sun and the thermal mass of the pavement. A refractive inversion causes light to bend upwards, not downwards. The opposite happens with a temperature inversion. When the air at the surface is colder than the air above it, the lapse rate is inverted, and the colder, denser air at the ground adds to the already natural air density gradient. This enhanced air density gradient causes the refractive conditions to be amplified, and it causes light to bend more sharply downwards. Finally, not all terrains are created equal. A series of rolling hills will have equal heating for nearly the entire day between the peaks and the valleys, driving local refractive conditions similar to a large open expanse. In the case of this photo, what appears like a labyrinth of canyons creates valleys that should create local conditions vastly different than elsewhere. Conditions like larger, shaded areas protected from winds, priming that terrain for far more pronounced temperature inversions after overnight cooling. Is this what necessarily happened? I'm not saying it has to be the case, but I suspect that during the day, the region would overall heat up. But with direct sunlight exposure to the peaks for a greater period, they would heat up more than the valleys below and retain that excess heat due to the thermal mass of the ground. During the night, and specifically just before the sun rose that morning, as the heat over the entire landscape radiated back out into space, the ground would cool down and cool the air. The cold air would roll downhill and settle in the valleys, and with the valleys already colder to begin with, the cooling effect and the existing temperature inversion should be amplified more than usual or would be typical elsewhere. Protected from winds, those valleys would naturally hold on to and create a larger, colder region extending above the peaks, producing conditions favorable to the required refractive conditions. I envision the effects are a stable temperature inversion inside the valleys that expands outwards above the mountaintops, similar in concept to the Wi-Fi logo. So there you go. What started as an investigation into a couple of questions I had turned into a detour that never entered my mind, to consider how the local topology might push atmospheric conditions a certain way beyond one's expectations. Also, in the process of recreating the Pic Gaspard photo, all indications point to their position being on the eastern side of the plateau of Finestrelle. One final, well, that was unexpected moment came when ChatGPT mentioned that this lowercase k refraction is almost exactly the classic 4/3 approximation. The uppercase k equals 4/3 strong refraction model used in radar and radio propagation. This was the sticking point in an MC Toon debate with Solly, I believe, who the flat earther in question kept arguing for a k equals 4/3. Anyway, that's going to be it for now. Thank you for watching, and if you like the video, you know what to do. And with that, I'm going to see you again in a video, hopefully soon enough. Bye for now.